example of what's called a field extension. I'm going to write Q in a fancy way. This does represent the rational numbers. The rational numbers do form a field under ordinary addition and ordinary multiplication of rational numbers. Remember, rational numbers are ratios of integers, fractions, in the usual sense of the word. You add the fractions by getting a common denominator. You multiply the fractions by multiplying their numerators and multiplying their denominators, right? That's things that you've known since 4th, 5th, 6th grade. Does form a field. That field, you might say, is defective in some ways. Defective field. That's not an official definition. There's plenty of polynomials, even quadratic polynomials, with integer coefficients that do not have roots in Q. As one particular example, leave some space up here, I'm going to write under here. X squared plus 2, for example, or let's do x squared minus 2. X squared minus 2, it is an element of Zx, which is a subring of Qx. I'm writing it as a subset, but it is also a subring. It's a subring of Qx, but x squared minus 2 is irreducible over Q. Can I find a bigger field in which it's reducible? You can factor it as x minus square root of 2 times x plus square root of 2, but square root of 2 is not a rational number. Those are real numbers. I could say x squared minus 2 is reducible over r. So x squared minus 2 is reducible over r. So the answer to whether I can find a bigger field over which this polynomial is reducible is yes, you can. R is one example. However, it's not the most ideal example for us. What's a more ideal field for us? No pun intended with ideal. What's a more ideal field for us with regard to doing field theory here and understanding factoring? A more ideal field is this one. Q, when you see the symbol, you say Q adjoin square root of 2. Q adjoin square root of 2. And here's a point of confusion for many people, including me when I was first learning this. I initially thought this was the rationals, take all the rational numbers, and just add one element, square root of 2. No, it's not that. Okay. It is, as a set, the set of all numbers of the form a plus b times square root of 2, where a and b are rational numbers. That's what it is. And that does contain square root of 2, but it contains plenty of other things besides square root of 2 that are not rational numbers, like 2 square root of 2 and 3 square root of 2 and square root of 2 over 2, or 3 square root of 2 over 2, square root of 2 over 3, 5 square root of 2 over 3, negative 17 square root of 2 over 3. And in fact, it's the rationals plus infinitely many more elements. Though there are plenty of real numbers that are not in here. For example, square root of 3 is not in there. Square root of 5 is not in there. This does turn out to be a field. In fact, it's something called a field extension of Q. It is a bigger field than Q. It contains Q. Q is a subset of Q root 2. In fact, you could say it's a subring or even a subfield of Q root 2. It is also a vector space over Q. Q adjoin square root of 2 is in fact a vector space over the rationals Q. A field can be a vector space over a subfield of it. Weird. So it's like the field is the vectors, the bigger field, and the subfield is the scalars. Weird, but true. And actually very important. We could ask, what's the dimension of this vector space? And I'll tell you, I'll let you think about it from the reading. It's two-dimensional. Any basis has two elements. What elements would those be? I'll let you think about it. Have a good day.